In the previous video, we discussed Lagrange interpolation, and we showed that if your grid points are equidistant, then you can run into Runge phenomenon as the order of polynomial interpolation increases. The workaround we discussed was to use a Chebyshev grid with Chebyshev grid points, or to use a piecewise polynomial. So in particular, in this case, for this function, often called the Runge function, we run into Runge phenomenon near the edges of the grid if we use a single polynomial to cover the whole grid. But if we use piecewise interpolation, then we can use smaller pieces of the grid and interpolate each of those pieces separately with different polynomials. To do that in Mathematica, instead of the interpolating polynomial command, we can use the interpolation command. So I can type interpolation and then plug in the data in pairs of x and y, just like we prepared it last time. These are pairs of data points x1, y1, x2, y2, and so on. So if we give that to Mathematica, then Mathematica would create an interpolating function. And if we click on the plus here, we see that Mathematica chose a third order method, a third order polynomial to interpolate those grid points. And I can set that equal to some function. Let's call it pp, which stands for piecewise polynomial. And then we can try and plot this. So I can say plot pp of x with x going from a to b. And we see that now we don't have Runge phenomenon anymore because the order of the polynomials we're using is low. It's a third order method, and we applied piecewise in small bits. So we can plot this against the data points if we use list plot, just like before, and then show the two plots together. Okay, so now in this video we're going to talk about finite difference methods. So finite difference methods can be derived by applying piecewise polynomials in each bit of your grid and differentiating them. So as we remember from our concept map, based on interpolation, by differentiating or integrating those polynomials, we can obtain numerical schemes for numerical differentiation, and so on. In particular, given a Lagrange interpolating polynomial of this form, where fj are the data points, the function values at xj, and pj of x is the Lagrange basis polynomial that we discussed last time, one may evaluate the derivative p prime of x by simply taking the derivative of these Lagrange basis polynomials. Since fj is a constant, the derivative only sees these polynomials. And if we evaluate this expression at a node x equals xi, then we obtain this expression. What we see here is pj of x prime. Prime stands for differentiation with respect to x, and then we replace x with xi. It may seem a bit confusing. Don't take a derivative with respect of xi here. It's a derivative with respect to x, and then we substitute x by xi. You can do the same thing with higher order derivatives. So if you take the nth derivative of this polynomial, then that amounts to taking the nth derivative of the Lagrange basis polynomial pj of x and substituting x equals xi. So for example, let's consider a Lagrange interpolating polynomial of order 2. That's a polynomial that interpolates 3 grid points. If you apply this formula, the Lagrange interpolation formula, and differentiate it, and evaluate the derivative at the middle point, then you obtain this expression. This expression is valid for any grid. The points don't have to be equidistant. In the special case where the points or the nodes are equidistant and the spacing is delta x, then this expression simplifies considerably, and you see that it's simply the slope. If you take fi plus 1 minus fi minus 1 divided by 2 delta x, which is the spacing between those 2 points, and the contribution from the middle point drops out for an equidistant grid. Similarly, if you want to obtain a scheme for evaluating the second derivative, you can do the same procedure, evaluate a Lagrange interpolating polynomial, take its second derivative and evaluate it in the middle, and then you can obtain this expression, which is valid for an equidistant grid again. Okay, so let's return to Mathematica and look at a few examples of how to construct numerical schemes for numerical differentiation. So let's construct a set of grid points and function values, and let's pick a set of 5 grid points. If we use the Mathematica command interpolating polynomial and use this list of pairs of grid points as argument, and we can ask for the polynomial to have z as argument, then Mathematica will construct the Lagrange interpolating polynomial that goes through those 5 points as described in the Lagrange interpolation video. And we can set this polynomial equal to pz, and then we can perform numerical operations on this polynomial. For example, I can evaluate the derivative at the middle point x2, and let's try this. So all I have to do is say p prime of x2, and we can ask Mathematica to simplify this expression. And we get a slightly complicated expression. This expression is of course going to be simplified if the grid is equidistant. So let's do that. Let's tell Mathematica to evaluate this last expression, assuming that the grid points are equidistant and that the grid spacing is equal to h. So x3 will be replaced by x2 plus h, x4 will be replaced by x2 plus 2h, and so on. So if we evaluate this last expression, percent means the last expression, and slash dot means substitution, and then these are the substitution or replacement rules. And then we ask Mathematica to simplify this expression. Then we get a well-known finite difference formula that's 4th order. So it's based on 5 grid points, and it's based on a 4th order polynomial. Remember, if you have a 4th order polynomial that has 5 coefficients, which can be used to fit 5 points or interpolate 5 points. So this method is formally 4th order. We could directly arrive at this formula a bit quicker with this command. So we can ask Mathematica to build a table of grid points like before that are equidistant, and there's a multiplication here space or multiplication, we can use star for the multiplication to be explicit. And then we evaluate the derivative. We construct the interpolating polynomial and use z as argument, and then differentiate that with respect to z, and then substitute z by the middle point x2, and then simplify, and then we get the same expression as before. And we can rewrite this a little bit more generally. So here I assume that we're computing the derivative around the point x2, but you may want to get a formula that you can use in your code which will have some index. So for example, an index I. So let's assume that I is the centered grid point, and we want to evaluate the derivative at that point using information from the function 2 points left and 2 points right of that point. So we repeat the same calculation as before, but replace 2 with I here. And remember, k runs from -2 to 2 in steps of 1. And that step is not necessarily to include, the default is steps of 1. So we could omit this argument here. And here is the same formula, just slightly different symbols that you can use in a code that uses finite difference methods using the index I. Now, Mathematica has a very nice tutorial on the numerical method of lines, and there's an article published on this framework, and I highly recommend going through this. I will post a link under the video below. And you can look at how the method of lines works, how you can solve PDEs, partial differential equations, based on finite difference or pseudospectral methods. We will cover this in a future video, but for now it's very useful to look through this tutorial and look at the formulas here, the finite difference formulas, and how to derive them. Let's go ahead and demonstrate how you can construct finite difference formula automatically with Mathematica. So to construct these formulas automatically with Mathematica, one can use the NDSolve finite difference framework, and then specify the order of the derivative that we want. In this case, let's suppose we want the first order, the first derivative, and then specify the list of grid points and function values. And then the finite difference order that we want. So in this case, we were doing fourth order differencing, but we need more grid points for that. So first, let's do second order differencing. So a second order polynomial has 3 unknown coefficients. If you use the method of undetermined coefficients to interpolate, then those 3 coefficients can be used to fit 3 data points. Or you can use the Lagrange interpolation formula to fit those 3 data points, and then differentiate that second order polynomial. So that's a second order method. And if you do that and evaluate the derivative in the middle point or the left point or the right point, then you will get 3 formulas for the derivatives of those points. And Mathematica can give you those formulas automatically if you call this function. So we hit shift return, and indeed we get the finite difference formulas at the first or the left point, and then the middle point, and then the point on the right. So let's see if we can obtain the formula that we got earlier when we were using 5 points with fourth order differencing. So if we use 5 points and use let's say fourth order differencing, then we get this expression, and this looks a bit more complicated. because it gives you the derivative at all those points. So it's a list of derivative values at each of those points. So let's give this list a name. Let's call it derivatives. Well, let's call it df. And let's ask for the value at the middle point. So we want df of not the first, not the second, but the third point. And then we can try the replacement rules that we had before. So these are the replacement rules we had before, except now we need to adjust them a little bit because this time we're using different notation. We start from -2. So let's try and fix this. Okay, so this means that x1 will be x0 plus h, x2 will be x0 plus 2h, and then x minus 1 will be x0 minus h, and then x minus 2 will be x0 minus 2h. And let's see what we get. And sure enough, we get the same expression as what we had before up here when we directly differentiated the polynomial. It's also useful to construct a differentiation matrix based on these formulas. If we go back to our slides, we see here that when we compute the numerical derivative based on Lagrange interpolation, we're constructing actually a matrix. We can call this matrix dji with indices j and i, which represent rows and columns respectively. And then when we sum over the index j, actually I would call this matrix dij, and then the summation over j amounts to matrix multiplication. So if dij is a matrix D and fj is a vector f, then this operation is simply d dot f, and we can therefore compute numerical derivatives by doing a simple matrix multiplication where the differentiation matrix D operates directly on the vector of function values and then returns a vector of the function derivatives at those grid points. So let's try and do that in Mathematica. Okay, so to construct this matrix, we could obviously construct the Lagrange interpolating polynomials according to the formula I just showed, and then take the derivatives and construct the matrix. Mathematica can do that automatically for us. So the way to do that is to use the same command as before, which was dissolve and finite difference derivative, and then the order of derivative. Then we provide the list of grid points, but now we're just constructing the differentiation matrix, so we don't need to specify the function values. So what we do is we specify the derivative order here, then the list of grid points, and then we just say what order of finite differencing we want. So remember, this is the order of the derivative, first derivative matrix, and this is the finite difference order that has to do with the order of the polynomial that we use for approximation. So that's the accuracy of the approximation. So let's provide a list of 7 grid points here and ask Mathematica to compute a finite difference derivative matrix based on a second order method. And then we apply this this function onto this word here, this string differentiation matrix. And if we do that, Mathematica returns a sparse array object. And it's sparse because it's full of zeros. If you click on it, you can look at the individual entries. To convert it into a usual matrix, you can use the command normal. And then you can see the elements. So some of them are 0. It's not very efficient to use it in this form. It's better to, for numerical purposes, it's better to keep it in sparse array form. But for purposes of demonstrating this, we can use normal, and then we can also say matrix form to write this matrix in usual matrix form. And we see that this is a banded matrix with zeros everywhere except for the main diagonal and the super diagonal and this under the main diagonal. So basically what's happening is that we build a polynomial, a piecewise polynomial, and we use a grid point on the left and a grid point on the right. So let's take this, for example, the middle point. It uses the point on the left and the point on the right to construct the finite difference formula for this center point. And then we move along to the next point. Let's go here. The next point, and again, we use the previous and the next point and construct an interpolating polynomial and evaluate the derivative in the middle, and we get this expression. And we go like that and cover the whole grid. The problem is that on the first grid point, you don't have a grid point left of that to use. So instead, we use the first, the second, and the third point, and then evaluate the derivative on the leftmost grid point based on that. So that's a right or left-sided derivative. So that's the reason why this matrix doesn't have a 0 here. So these zeros stop right here, and then you use one-sided derivatives for the first point, and the same is true for the last point. So over here you have to use a right-sided derivative to compute the finite difference derivative. So this looks a bit complicated, so let's simplify it, assuming that the grid points are equidistant. So again, we provide a list of grid points, and we want the first order, the first derivative matrix, and we want to use second order finite differencing. So if we type this command and then shift return, we obtain this matrix, but simplified, assuming the points are equidistant. So it's a bit simpler. And you see now that the main diagonal is 0 because, as mentioned earlier in the slides, for equidistant grids, the middle grid point cancels out. So we have 0. And then this formula is the same as what we had in the slides for the finite difference derivative with second order method. And again, the first and last grid points use one-sided derivatives. So the structure here is a little bit different. We can build this command into a function. So let's create a function with delayed equals, which takes the order of the derivative that we want as input and the list of grid points. And you can hard code, if you want, the difference order of your method, the accuracy of your method. So let's suppose we want to construct a method using second order finite differencing that returns a derivative matrix of any order. So let's try and apply this matrix onto this list of grid points that we used earlier. And again, this will return a sparse array. So let's use normal and matrix form to display it in the usual form, and we obtain this matrix. So it's slightly different than before because I used D2 here. That's a second order derivative matrix. If we want D1, that's the first derivative matrix, then we get the same result as before. If we want a matrix that calculates the second derivative, we can simply replace this by D2, or if we want the third derivative, we replace this by 3, and so on. Okay, so let's try and test this derivative matrix and compute the derivative of a known function. So earlier we computed the interpolating polynomial going through these points. So we had a set of grid points x and the function values y. So we already have those evaluated here. So let's try and evaluate the derivative. So the derivative will simply be, we don't have to repeat this, but we have to evaluate the derivative value. So we can simply say f of x are the function values, and we can evaluate those as numbers, floating point numbers, by using n. And then we can calculate the derivatives at those points. And because the function is listable, I can simply replace the argument by capital X, where X is the list of grid points. And here we'll get the exact derivatives that we can compare to. And again, I can convert those to floating point numbers. So let's suppose we want to calculate the first derivative. Then I can simply say d and 1, and the argument needed here is the list of grid points. So it's simply x. So that returns a sparse array, and then we can simply dot that sparse array onto the function values that are f of x. We have already set this equal to y. That's the list of function values. So by dotting this derivative matrix onto the function values, we get an approximation for the derivative. And this is what we get here. Because the grid points were integers, Mathematica is treating this symbolically, so it returned fractions here. But again, we can use n either on the whole expression or simply on the function values, and possibly the grid values to evaluate the result numerically. So let's do it on the whole expression, and these are the derivative values approximated using second order finite differencing. So to get a sense of how accurate this is, we can compare to the exact expression here, where we calculate the derivatives exactly. So let's call this dy by dx numerical, and then let's compute the difference of the numerical result compared to the exact result. And we see that the difference is relatively small. And of course, if we want higher accuracy, we can see that there are a few points that are 0.2, 0.3. We can calculate the absolute value of those points, and then calculate the total error or the mean error. So that is proportional to the L1 norm. So the L1 norm will be summing all of those points. So the L1 norm is the summation of all the errors without dividing by the number of points. So that's the reason why the mean is slightly smaller, because if we divide the total by the number of points, then that gives us the mean. So the mean is a bit smaller. If we want higher accuracy, we can go back here and increase the order of the difference order. So that would use fourth order polynomials or 5 points to calculate the derivative matrix, and it would do it in a piecewise manner. And then if we calculate the derivatives again, hopefully they will be a bit more accurate. So indeed we see that now the error is much smaller, and we don't run into trouble by increasing the order of the method, because these are piecewise polynomials, so they're applied in this way in a small number of nodes, and then we move to a different polynomial as we switch nodes. And each of those polynomials is centered at the grid point where we evaluate the derivative. So it can be shown that the derivative approximations are more accurate at the center grid point when you have 2 points on the left and 2 points on the right, whereas one-sided derivatives like these have a slightly higher error. So centered differences are usually the best to use, with few exceptions. And finally, we can look at a list plot of the error, just to show where the error is localized, and we see that the error is slightly higher in the middle and slightly lower at the edges of our grid. And finally, one can do convergence testing. So let's first of all, because x is already specified, let's clear its value, and let's construct a set of grid points that depends on an argument n. So that will build a list of grid points for different sizes, and then we can call that function to build a vector of different sizes. So for example, x of 5 would be would build a list of grid points of 6 grid points that we can fit with a fifth order polynomial. So n is the order of the polynomial that will that one can use here. But in fact, we'll construct piecewise polynomials for different values of n. Okay, but I will not complete this part because this is part of the exam. So it will be left as an exercise for now, and we will show the solution to how to do convergence testing for finite difference methods in a future video. The last thing I want to show is how to do the same operations in 2 dimensions. So for example, let's suppose we have a set of grid points in the x and the y direction, and then we construct a Gaussian with the values of those of the Gaussian at those grid points. And we can use the outer command. If you are not familiar with that command, you can type question mark and then outer. And you can see that the outer command can apply any function onto a set of lists. In a sense, it's an outer product. So this constructs a higher order tensor. So if we have a set of grid points xi and a set of grid points yj, then outer will with g here as argument, we'll apply this function g and construct a set of points g of xi and yj. So in this case, it's a two-dimensional matrix. If we had more lists, if we do it in 3D, then it would be g of xi, yj, and zk, and so on. So we would have a third argument here in the list. So we need those values, those function values, and the grid points to construct an interpolating polynomial and do the finite differencing, and then compare to the exact derivative to see the accuracy of our method. So we can simply use the n-dissolve finite difference derivative function of Mathematica again, and specify that we want the first derivative with respect to x, the first derivative with respect to y, and then specify the grid points x and y, and then the function values, and then finally the finite difference order. So here let's pick 2, and we can use listplot3d to plot those derivatives, and this is the result. We can also look at the error by comparing to the exact result. So to look at the error, we would calculate those numerical derivatives and then subtract the exact result. So to get the exact result, we can use analytical differentiation of the Gaussian with respect to x and y, and then evaluate this inside here, and we put this inside a function so that this gets evaluated and then treated as a function. So Mathematica, because of the evaluate command, it will first evaluate this and then do the plot. If we didn't do this, then it would be really slow, because for each and every point, Mathematica would have to do a symbolic differentiation here. That would make your code really, really slow. So we want to use evaluate in order to force this symbolic calculation to happen now. So it happens first, and then it constructs this function, and then it does the outer product of this derivative function, and then it's applied to the grid of x and y. So it's evaluating those derivatives with respect of x and y, and then we do a list plot of the difference between those values and the values obtained numerically. And let's do it for a second order method, and we see that the error is around goes from minus 0.01 up to 0.01. And if we want to have a more accurate approximation, we can use a fourth order finite difference method, and you see that the error goes down a lot. You don't need to specify the difference order, so if you leave it unspecified, Mathematica will pick a value for you, and the default it picks, I think it is 4. So you see that you get the same accuracy here as if we pick a fourth order method. And if we pick a higher order method, like a sixth order method, then the accuracy gets better. But it's dangerous to keep increasing it, because finite difference derivatives are sensitive to the accuracy of the function values themselves. So you may run into trouble if you keep increasing this. So this is it for this video. Thank you for watching. And if you want to find out more about these n-dissolve finite difference methods, you can see this tutorial that is going to be linked below.